Hello class. I want to use this opportunity to explain some of the free rotation chain. So in the classroom we actually discussed about how free rotation chain end-to-end distance h square is equal to nl square average 1 plus cosine theta 1 minus cosine theta. And theta by definition is this angle, okay? And we didn't really explain much details about what is this value, okay? So in this particular lecture I will address this derivative item. As I mentioned, it's a little bit complicated, so not everybody is required to understand that. So we talked about generally h square average end-to-end distance square is going to be equal to nl plus I equals to 1 to n, j not equal to I to n, and li lj square. So we call it, this is self term, and this is where li dot li will be, right? So, and we explain this second term is a cross term, and this describes every term which is not sitting in a diagonal of the matrix. So if we recall, this is a self term. This is 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Now we also have 1, 2, 2, 2, 2, and this is going to be 3, 1, 3, 2, and 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, 5, 3, 5, 4. So it's going to be a matrix, right? So we also learned about the cross product, right? Li multiplied by Lj will be equals to dot product will be L, which is individual bond lengths, multiplied by L, multiplied by cosine theta I minus j power, right? So it's kind of easy to understand. If you have a bond going one direction, each time it's connected bond, you have a cross cosine theta angle component in there. So if this is 1, 2, 3, so if you consider 1 and 2, which means I would be equals to 1, j would be equals to 2, so I minus j would be equals to 1. So you're going to have L square dot cosine theta once. But if you consider for bond 1 and 2, so for bond 1 and 3, what you're going to have is now consider this bond and this bond. So I going to be equals to 1, j going to equals to 3. So your projection now will be L cosine theta square, because it's going to be project once to bond 2 and project again to bond 1, right? So this can be generalized as Li dot Lj for any bond along the polymer backbone will be equals to cosine theta n times. So if we just define alpha will be equals to theta, just for me, so I don't need to write cosine theta again and again, then this will be equal to L square alpha I minus j. Okay, so now the second part of the process is to understand how many components is in there. Now let's consider how many in this matrix, how many I minus j will be equals to 1, or basically close neighbor for this matrix. Okay, so for this particular matrix, basically this would be equals to here. This would be equals to every component is not on the diagonal, right? So in this case, you will be able to extract who is I minus j is equals to 1, which means the bond is next to each other. So if you count, use this example, you will have 1, 2, 3, 1, 4, 3, 4, 5. And symmetrically, you're going to have 4, 5, 3, 4, 2, 3, 2, 4. And then you have 1, 2, 1, 3, 1, 4, 1, 5. Symmetrically, you would have the same on the top. So we're only going to consider half of the box, which is bottom half, circled in red. And if we multiply by 2, we will get the top one. So what we can do now is we can know there's n minus 1 number of the bonds which are closer to each other. Okay? So we would naturally get the equation given by this one. So this 2 means we consider symmetrically half of the matrix. And we're going to define this new term, k, n minus 1. K would be equals to I minus j. So if k equals to 1 means I and j are neighboring, they are next to each other, so which is this term. And we know there's total of n minus 1 of them. So we can just write this would be equals to L square of k m minus k. So take a moment to digest this particular equation. N is basically how many of them, and k is basically this value. So if we want to write this matrix out, I'm going to use a red color. We have basically 4, right? 1, 2, 3, 4. We have 4, which includes 1, 2, 3, 1. This is actually 2, 1. So you have 2, 1, 3, 2, 4, 3, 5, 4. So we have 4 L square alpha plus we have 3 L square alpha square. And what are alpha square? Which is 3, 1, 4, 2, 5, 3. So you got 3 number of these. Then you got 1, 2 of L square, which consider 4, 1, and 5, 2. And you have 1 number of 2 L square, no, just 1 L square alpha 4. So this lengthy equation basically summarizes all the possible metrics you would have. And if you multiply by again, on the top half, this is where this number 2 is coming from, is this is double upper matrix. Okay? So once we got this, rest is relatively easy. And now we just need to integrate what's the value for this particular part and this particular part. Okay? So why don't we do that? I'm going to erase this particular part. What you now going to have is going to be equals the bottom of this equation. We're going to